realize some of you were not here, may not have had a chance to make that up just yet. But today we're actually covering what the fundamental theorem of calculus says. So I need your attention, please. Thank you. Part 2 we've actually already learned in section 5.3. Part 1 involves what we defined yesterday to be an area function, where you have a function equal to an integral of a different function. So that's why we spent time yesterday going over what that function means, how to work with it, and then today we're actually working with what the fundamental theorem of calculus says. So what I have for the first example is to help us make sense of what part 1 of that fundamental theorem of calculus says. You can abbreviate that with FTC. But we are given if g of x is equal to the integral from some value a to x of f of t dt, where a is equal to 1 and f of t is t squared, find a formula for g of x and calculate g prime of x. So I am going to rewrite g of x, substitute in a and f of t. So I know g of x is equal to the integral from 1 to x of t squared dt. So really what this is asking, it wants to know what is a formula for g of x in terms of x, so not in terms of an integral of a different function. I can find the integral of this function. So when I find an integral, what am I actually finding? Antiderivative. Antiderivative of t squared is 1/3 t cubed, and that would be evaluated from 1, oops, it's going to start to write x, 1 to x. So then I can substitute in x, and I would have 1/3 x cubed minus, if I substitute in 1, I have 1/3 times 1 cubed. 1 cubed is 1, so I just have 1/3. Okay, so g of x is the function 1/3 x cubed minus 1/3. So find a formula for g of x. That is g of x. Then calculate g prime. So now that I know g of x, this 1/3?
Yeah.
If you substitute 1 in, then 1 cubed is just 1, so you would just have 1/3. It's always, yes, it's the antiderivative evaluated at this value minus at this value. So this would be like f of b minus f of a is how it's phrased. Then what is the derivative of 1/3 x cubed minus 1/3? X squared. Oh. Derivatives, yep, so switching your thinking. Derivative of 1/3 is just 0.
So is this just proving that f of t is equal to g prime?
Yes. Yes, so what we're supposed to get from this, so here's g of x, here's g prime of x. All this is showing is what the first part of the fundamental theorem of calculus states. It's showing that g prime of x is really equal to f of x. So from here, I'm just going to write this out. If I know f of t is t squared, if I replace then, let's say I find f of x, that just means I'm replacing the t with x, so f of x is x squared, and this just shows that g prime of x is equal to f of x. That's what this is proving to you or showing you here. So the first part of the fundamental theorem of calculus says that if f is a continuous function on the closed interval from a to b, then the function g, defined by an area function, g of x is equal to the integral from a to x of f of t dt, again on the closed interval from a to b, is an antiderivative of f, and we talked about that idea yesterday. That is g prime of x is equal to f of x on the interval from a to b. I left some space here. I wanted to show you how this would be written. They give this in the book as well, the Leibniz notation for this. So basically in words, I just want to explain what part 1 says. Again, and we talked about this yesterday, some of you I know were not here. The fundamental theorem of calculus shows the relationship between differentiation, finding a derivative, and then integration, finding an integral. They're inverse processes, so finding a derivative and finding an antiderivative are inverses, and that should make sense. So it says, this is really what part 1 is saying. If you first integrate a function f and then you differentiate the result. So you first find the integral, which is the antiderivative, and then you find the derivative of the antiderivative, you're just going to get back to your original function. So that's what we did up here. We first integrated f, and that's how we got g, and then we took the derivative, but it got us back to f. It got us back to f of x. It's just the variables are different, but we got back to the x squared. Okay, so the Leibniz notation just shows that if you have an integral from a to x of f of t dt, and then you take the derivative with respect to x of it, so the derivative with respect to x of an integral is just going to equal f of x. So you integrate f, then you take the derivative, you're just getting back to x, or just getting back to f. But do notice that your variable then, it is f of x, so it is going off of the variable in the upper limit here. Okay, so I did want to show you as well, you're not asked to mimic any proofs on my test or the AP test, but I wanted to show you why this makes sense as a proof. We just saw a specific example of why it makes sense. But if we start out with, this is a more general example, I suppose. So g of x is the integral from a to x of f of t dt. What we had just done above with a specific example was we said to find g of x, we are finding the antiderivative of little f, which we could call big F, of t, and evaluating it from a to x. And this then is equal to capital F of x minus capital F of a. So evaluating it at x minus evaluating it at a. So that's a general form of g of x. So then if you wanted g prime of x, that is then, and I'm going to write the derivative, or show the derivative of the integral as well. That's taking the derivative with respect to x of your integral. But that means because we said the integral was equal to capital F of x minus capital F of a, you're really taking the derivative with respect to x of capital F of x minus capital F of a. And so then the derivative with respect to capital F of x, that is capital F prime of x. F of a is a constant, so the derivative of a constant is 0. And then capital F is always defined to be the antiderivative of little f, so capital F prime is just little f of x. So that's showing how we're getting to just f of x. That's usually what they include after a proof, just to show the proof is done.
Fancy.
It's a square period. Sure. That's what they were saying. Yes, usually after a proof, you'll just see a little box at the end to show the proof is done. Proof is complete. So here's how to use it. That's what it is. Understanding the idea is important. Now, it might help your understanding to actually see how to use it. It says use part 1 of the FTC, Fundamental Theorem of Calculus, to find the derivative of the following. So if you have g of x is equal to the integral from 0 to x of the function square root of 1 minus t squared dt. So in this integral, f of t is the function square root of 1 minus t squared. So if I am finding g prime of x by the first part of the fundamental theorem, that is just equal to f of x. So it's equal to the square root of 1 minus x squared. And that's my derivative. So I don't need to find the integral and then find the derivative like we did for the first example. Knowing that it's going to equal f of x, I can just go straight to f of x. Okay, are there questions on this? It does not matter what your lower limit is. So in example B, g of x is the integral from 3 to x of 1 over t plus t squared dt. The 3 does not matter. G prime is still just going to equal f of x. So it's going to equal 1 over x plus x squared. Okay? Because it's not all derivatives of integrals. Okay, now the next example is not just like this, okay? This is part of it. Look at example C. What's different? I heard it. The cosine of x is different. This is not just x like it was in the definition. Okay, that matters. If your upper limit is a function itself, it's not just x, we can't just say then g prime equals f of x. Okay, so I'm going to show you, rather than just saying this is what it would equal, I want to show you why. So we're going to go through this one like we went through the very first problem. We're actually going to find the integral and then find the derivative. So you can see why it works out the way it does. So finding the actual integral first. What is the antiderivative of 1 plus t squared? Yep. Okay. Evaluate it from 1 to cosine of x. Okay. So if I plug in cosine of x, I will have, I'm going to write this as a quantity, two separate quantities here. So if I plug in cosine of x to the entire thing, I have cosine of x plus 1/3 times cosine of x quantity cubed. So make sure the x isn't just being cubed, the entire cosine of x is being cubed. And that's just if I plug in cosine, so then I have to subtract what I get if I plug in 1. If I plug in 1, I'll have 1 plus 1/3. So yeah, 1 and 1/3, 4/3. Wait, is there a question? Oh. Okay, so I'm going to write this without the parentheses. So we have, altogether we have cosine of x plus 1/3 cosine of x cubed. You could write that as cosine cubed of x, and then minus 4/3. Okay, so that is g of x. Well, that's g of x. Now we have to find the derivative of that. And we will see it is not just going to equal what f of x would be. Our derivative is not just going to be 1 plus x squared. So it doesn't, because of that cosine, it's different than the previous examples. Derivative of cosine is negative sine. Going back to derivatives, not just antiderivatives. What about 1/3 cosine of x cubed?
Minus sine x.
It is a chain rule.
Oh.
Okay.
God.
So you have to multiply the 3 by the 1/3. So it would be plus.
Well, 1.
I know some of you are kind of combining things. So plus, it'd be cosine of x squared times the derivative of cosine, so times negative sine of x. And then derivative of the minus 4/3 is 0. So that is the derivative. You can see it is not 1 plus x squared. It's not f of x. However, I'm going to rewrite this because I could factor out a negative sine of x. So I have negative sine of x times the quantity 1 plus.
Can you see it 4/3 back? Oh, that's
Yep, that would be an antiderivative. If I factor out negative sine of x, this would just be 1. This would just be cosine of x squared. I'm going to write that as cosine squared of x. Okay, does anybody see a relationship? We can't just say the derivative would be f of x. But notice, instead of having 1 plus x squared, we have 1 plus cosine of x squared, essentially. So this part is really f of cosine of x. So it's evaluating our function f by substituting in the upper limit. So if f is 1 plus t squared, this piece here is really as if I just substituted cosine of x in for t. And then the negative sine of x is the derivative of cosine of x. Okay, so it's the derivative of the upper limit. So it's kind of like you're using a chain rule. If your upper limit is more than just x, in a way you're using a chain rule. So here's kind of a separate rule. If you have a function g of x where your upper limit is more than just x, so I'm going to write it this way. Say you have g of x is equal to the integral from a to some function h of x, so it's more than just x, of f of t dt. Still by part 1 of the fundamental theorem of calculus, so that you don't have to do this process every single time, you can find g prime of x by finding f of h of x times h prime of x. Okay, so the f of cosine of x here would have been the f of h of x, and then the derivative of cosine here would have been the h prime. So this is kind of a separate rule. And that rule would still apply if this was just x. This would be f of x. The derivative of x is just 1. So this rule would still apply even if your upper limit was x, kind of tying that into what the first part actually says. So here's how to use it. If you look at example D, g of x is the integral from 1 to x to the 4th of secant of t dt. Okay, the upper limit is not just x. It's more than x, so you need a chain rule of sorts. This is kind of the chain rule for the first part. So f of t is secant of t. So here's g prime without having to do the entire integral and then find the derivative. It's equal to f, well maybe I'll write it out this way, f of x to the fourth times the derivative of x to the fourth. And this you don't have to write out every time, I just want you to see where it's coming from. So I would have secant of x to the fourth times the derivative of x to the fourth is, oops, not 3, 4x cubed. Okay, or you could write it as 4x cubed secant of x to the fourth. So that would be g prime. Okay, so do part E. I won't walk around, but then we'll just check it. Find g prime for part E. Are we okay if I show the answer? You can check. You all have an answer. See if it's right. No? Negative sine of x times the cube root of 1 minus cosine squared of x. With sine squared, yes. So you could, because 1 minus cosine squared of x is sine squared of x, so you could, an alternate answer could be this. This is how it would look. This would just be the simplified version. Nothing cancels out, but you could rewrite it that way too. So the idea with the first part is if you have, or here's kind of the goal that we talked about yesterday as well. I have the entire fundamental theorem here. So you're supposing f is continuous on the closed interval from a to b. The first part says that a derivative cancels out an integral. So if you take the derivative of an integral, you're canceling out those operations to just get your original function f. You should also be able to recognize when you have a function of this form like we talked about yesterday, if g of x is equal to the integral of another function, g of x is really the antiderivative of f. So we talked about that relationship yesterday. That's because the derivative of g is actually equal to f. The second part we talked about in 5.3, that says if you take the integral of a derivative, it cancels out and you just get the original function. So if we had the integral from a to b of f of x dx, I could rewrite f of x, or little f of x I should say, is equal to capital F prime of x, since capital F is the antiderivative. Because then this integral shows that you're taking the integral of a derivative, an integral of a rate of change, and that just gets you back to the original function. The integral and the derivative cancel out to just give you capital F of x evaluated from a to b. But that was the evaluation theorem, or that total change theorem we talked about in 5.3. So using the fundamental theorem of calculus part 2 is what you did in 5.3. There's nothing, no new special way, it's just telling you what it is. So overall, this just tells you derivatives and integrals cancel each other out. That's the main idea. And I do have some practice. This practice is mainly, it might all be, I'd have to double check with the last couple. This is, because you've already had practice with part 2 and 5.3, this is practice of what we covered today with part 1. So using part 1 to find the derivative of functions evaluated as integrals.